Here's a function. It's a nice simple function, f of x equals 1/2 x squared plus 1. And let's say you wanted to know the area that this function captured over a certain interval. So what I mean by that is, imagine that we're going to shade below the function, and we do this on a, let's just say the interval from x equals 0 to x equals 3. So let's say we're just wondering what is this area over here. It says over here that it's 7.5 units. Just ignore that for a minute. Let's imagine you didn't know that it's 7.5 squared units, and you wanted to find an estimate for how much this area is. We're going to do that using rectangles. So I'll start with something nice and simple, and let's say 2 rectangles. So I've made 2 rectangles that are underneath the curve here. Notice that each of those rectangles touches the curve at its left, upper left corner. It touches the function. That's why it's called the left-hand sum. If we make more rectangles, you'll notice the amount of wasted space gets less and less. So as we increase the number of rectangles, we get a better estimate here for what that area is. Okay. Notice also here that all of the rectangles are underneath the curve. So if we calculated the area of all these rectangles, it would definitely be an underestimate of the actual value of this area here. Alternatively, we could do a right-hand sum. So notice this time all of the rectangles are above the curve. And the reason for that is because now we're matching up the right corner, the top right corner of the rectangle with the function. Okay, so again, if we wanted to get an estimate, we could find the areas of these rectangles and add them up, but this time we would get an overestimate. So we would get an estimate that is more than the area under the curve. Okay, so that's what we're going to do next. We're going to try to approximate this area by calculating an underestimate like this and an overestimate like this, and then that should give us a reasonable idea of what is the area under the curve. So if we're going to estimate all of the area that is covered by these rectangles here, we're going to find each area individually and then add them all together. I think the best way to do that is to organize things in a table. That's how I like it anyway. I think it just helps keep everything organized. So that's what we're going to do here. So to find the area of a rectangle, you need to know the width and the height. So in my table, I have 6 columns because we've got 6 rectangles, and we're going to find the width of each rectangle, the height of each rectangle, and then multiply those two values to find the area. Because I have 3 units on my interval here, and I've split that into 6 rectangles, that means each rectangle has the same width. They all have a width 0.5, right? That's just 3 divided by 6. The height of each one of those is going to be different. Now, this is where it becomes very, very useful in drawing a picture, because if I want to know the height of this rectangle, well, this first one is easy just by looking at the graph. You can see that it's 1. But what's really important here to notice is that the height of this rectangle is the same as the value of the function at x equals 0. Right? Because this rectangle matches up with the function at the point where x is equal to 0. So the height of the rectangle is f of 0, right? The value of the function when x is equal to 0. If I want to look at the second rectangle over here, it's not as obvious to see what is the height of this rectangle. So what we need to do is find the height by using this part of the function. This is where the rectangle and the function have the same height. The x value of this point is 0.5. So the height of that point is f of 0.5. Right? The value of the function when x is 0.5. Similarly, for this third rectangle, the height is at this point here on the function, and that is, if I trace that down, that's f of 1. Okay, and you'll start to notice a pattern from here. The fourth rectangle has a height of f of 1.5. The fifth rectangle has a height of f of 2. And the sixth rectangle has a height of f2.5. Okay, so then to calculate each of these heights, you just need to plug in these different x values into the function. I'm not going to do that. You've been doing that for years and years. So when x is 0, the function is equal to 1. When f is 0.5, the function is 1.125. When x is equal to 1, the function equals 1.5. When x is equal to 1.5, the function is equal to 2.125. X is 2 gives us a value of 3. And f of 2.5 is 4.125. Okay, so now we know the widths and the heights of the rectangles. All we need to do now is multiply each of those pairs together to find the area of each rectangle. So the area of the first rectangle is 0.5, and so forth. I'm not going to talk you through these. You can put them into your calculator to double check to make sure that you agree. Okay, so we have the area of all those 6 rectangles. Then the final step is just to add them all together. And if you do that, you will find that the total area of those rectangles is 6.4375 square units. I'll re-emphasize again that because this is a situation where all of the rectangles are below the function, this is called a lower bound estimate. It's the smallest possible area that we could have under the curve. As you can see, these little white gaps imply that there is more area involved here that we haven't actually calculated. Okay, so we can also look at an upper bound as well. And we're going to do this in exactly the same method. Okay, so notice here, this time all of the rectangles are drawn above the function. And that's how we know it's going to be an overestimate. So we call it an upper bound estimate. Okay, again, the process is going to be the exact same. So I'm going to go through it a little bit more quickly. If you want to, you can pause and check to make sure you understand how to do this, and then click unpause and see if your answers work out to be the same as mine. So I've got my table set up. Again, same number of rectangles, so they all have the same width of 0.5. This time the height of the rectangle, the first rectangle, meets the function at this point here. So that is the value of the function when x is equal to 0.5. So f of 0.5. The second rectangle has a height here at this point. So that means the height of that rectangle is f of 1. And the pattern continues. F of 1.5, f of 2, f of 2.5, and f of 3. Fortunately, all of these numbers we actually calculated in the previous example, so we don't actually have to do any new calculations there. Those are all the same. If you plug f of 3 into the function, f of 3 is equal to 5.5. So, again, we do the same process. Now that we know the heights of the 6 rectangles, we multiply those together with the widths. So, those are the areas of the 6 rectangles. Again, you will notice these areas here are the same as the areas of rectangles 2 through 6 in the previous example. They've just been shifted over 1. And if you add all of those up, you end up with a total area of 8.6875 square units. So just to recap, what we've done here is we found a lower bound of 6.4375, and we found an upper bound of 8.6875. So we know that the area is somewhere between those two. You might think maybe you can find the actual area by averaging these out. That might get you a little bit closer to the exact answer, but it's not really a proper mathematical method for doing it. So I would hesitate to go too far down that rabbit hole. Last thing we're going to talk about is how can you get this more accurate? Well, this is the situation when we've got 6 rectangles. Here we've got 8 rectangles. Here we've got 10 rectangles. And hopefully by this point you're seeing that as we add more rectangles to the party, these rectangles are getting closer and closer to the value of the actual function. So if we increase the number of rectangles, we get a more accurate estimation. And if we increase that enough, eventually we get super, super close. Now imagine if you could do infinitely many rectangles. If you could do infinitely many rectangles, each rectangle would have a width that is infinitely small. And what you would end up with is you would end up with a nice smooth area that would be the actual area under this curve. And that's what integral calculus is all about.